I'll be talking about, most importantly, I'll be talking about what a simulator can and can't do for you. Okay, so firstly, why do we use process simulation? So I'm going to assume that most people who've signed up here are going to be process engineers or chemical engineers, and everyone has at least some exposure to process simulation. Either you're using it at work or you have probably used it for your capstone or final design project over in university. There's various tools that one may be used to: Unisim, HYSYS, Petrosim, Aspen Plus, GPROMs. Yeah, so there's a ton of things that people have. So if we look at a typical asset life cycle, by asset, I mean, it could mean everything from like an oil and gas production facility, gas plant, refinery, polymer facility. If we take a look at one of these assets, where do we find process simulation? Where do we typically use it? Well, generally, if you've got like a new opportunity, either to develop a new hydrocarbon field or build a refinery, you typically want to do some conceptual studies, feasibility studies, maybe some process synthesis. So you'd have need to get an idea of some of the heat and material balances, some of the fluid behavior, some of the fluid properties, to allow you to design various types of processes. For example, if you're taking a look at an upstream facility where you've got like a oil production facility, one of the things that you're going to encounter is multi-phase flow. You're going to get like liquids and gases coming in through pipelines, coming into separators. So you need to take a look at things like slug catchers for your front end. You might have like a compression system. So you'd be thinking about compression systems, gas lift, fuel gas systems, things to do with your gas. You need to have to probably dehydrate them, etc. So no, when you come across a new opportunity, you generally do some feasibility studies or conceptual design. At that point in time, you're definitely going to require some form of simulation, generally steady state type simulation. Yeah, steady state thermodynamic equilibrium based. Later, you might be doing some basic design or front-end engineering design, where you might be looking at refining your design or your flow sheet, taking a look at the type of equipment you have, sizing the equipment, distillation. Let's say, for example, you might be looking at separating some components. You look at sizing your distillation column, number of trays, rough idea of what your diameter needs to be. You need some hydraulic calculations to check to make sure that your trays aren't going to be flooding. Make sure that you've got enough like a hydraulic behavior in your trays to avoid your flooding or weeping, etc. So you'd be using some simulation. You probably still be using some kind of steady state simulation tool, maybe with some slightly more sophisticated equipment based modules or third-party modules. You might also be doing things like HAZOP at this point in time. So HAZOP is going to be pretty interesting because when you're looking at HAZOP or hazards identification, you might be looking at phenomena like a sudden valve closure. If I have a valve closure, something's going to happen. I might get an increase in pressure. Now we're starting to look at the time domain and system responses. So maybe you might start looking at a bit at some of the system responses for this kind of analysis, and you might turn to some kind of a dynamic model, yeah, or transient type model. And that could be anything ranging from MATLAB and Simulink all the way up to like full-blown HYSYS. Detailed design, you start getting more sophisticated in terms of the model because you want to understand operability. Is the system that I designed, the control scheme that I designed, the capacitance that I put in, either thermal capacitance or material capacitance, is it going to be enough to ensure that I've got like a smooth operations in my system? I want to ensure that once I've commissioned, if I want to commission the facility, I want to come up with like maybe a commissioning strategy or a startup strategy. That's when you start looking at dynamic simulation. Yeah. Sometimes you might want to start training your operators. Then you might want to take a look at some dynamic simulations which are coupled into operator training systems. Yeah. Later, construction. At this point in time, might be training some of your operators or getting ready for commissioning. Commissioning startup, you might do some troubleshooting. So you might typically around this area here, you might start using more dynamic simulation. Operations. So around here, you might have, I think a lot of people like to use the term digital twin. So I'm not in sales mode today. So you've got to be a bit careful when people tell you they've got digital twins, because it can range everything from like a simple steady state model to measure some form of performance, for example, turbine efficiencies, compressor efficiencies, or distillation tray flooding, to something far more sophisticated, which might also allow you to do some optimization behind there. Yeah. So one needs to be a bit careful when we're throwing around the term digital twin, because it's a term that salespeople like to use a lot. And it appeals to a lot of the MDs and CEOs. So when someone comes to try and sell you a digital twin or something, make sure you understand what they're talking about. But at the heart, that will be some kind of a model, either a thermodynamic first principle model, or even like a statistical neural net-based model. Okay. After you've been operating a facility at some point in time, you might want to check and do a revamp or debottlenecking study. Again, you might do that might be a steady state and dynamic type models. And then you might decommission. So as I've shown you, this is your typical life cycle for your facility. And that throughout the entire life cycle, there will be some form of computation and simulation required. Yeah. So sometimes people tell you that, hey, why don't you invest in a model somewhere in your feed, and then you can kind of like bring it over to training and operations, etc. And that is true. You can do things like that, but you need to be a bit careful again in looking at these kinds of solutions, because as you go from one level of rigor to the other, say for example, if you have an engineering model, that engineering model isn't really going to be suitable for training, or to be used as engines, or to be used as performance monitoring type system. So different types of requirements. Whenever you go through different areas over here, your model will generally change. The type of model might change. It could be something as simple as I built like some kind of a model at front-end engineering and I just modify it a bit, or I might have to completely build a different kind of simulation model for each one of these areas. So it's very, very important for us really to understand what the actual requirement is, because that will determine what kind of simulation environment we need to enable that. Yeah. Okay. So now, as an engineer, once you've understood your objective and what sort of mathematical relationships you need in order to get your solution. I guess in the old days, there were no simulation. I guess when I started my work, there were no commercial simulation applications. You have an objective and you start doing hand calcs. If you're lucky, you might have a spreadsheet or a computer to assist you. You had to do a lot of iterations by hand, a lot of like case studies or parametric analyses you have to do by hand, and those will take hours. So nowadays, we have process simulation tools which have kind of codified and gathered all of that information into a easy-to-use software or a computer-based environment. So it allows you to run through all of these types of old iterative calculations very, very quickly. Yeah. So they allow us to do a lot of repetitive iterative calculations and minimize any kind of potential human error from that. Yeah. However, we need to be really, really careful, as I mentioned earlier, that there's no one size fits all when it comes to simulation tools and engineering problems. So there's no one single simulator that can cover every aspect of real life phenomena, because things are very complex. You use something like HYSYS or Unisim or Petrosim, and these are thermodynamic equilibrium based tools. But real life isn't just thermodynamic equilibrium. You've also got mass transfer, momentum transfer, heat transfer, which bring things away skew things away from the ideality that thermodynamics typically represents. Hence, we really need to understand what some of the underlying principles and constraints are when we're working with the software tool. Okay. Yeah, so I kind of like this cartoon. Before I started my career as an engineer, as a consultant, I was working for the company that actually wrote HYSYS. It's a company called Hypertech. And one of the things I did in early in career, when I started off, I was like a tech support engineer. So I'd be the guy on the other side, picking up the phone or looking at the fax. This is before, back then we didn't have email. So I get a fax or I get a phone call, and I get all kinds of complaints. And one complaint that kind of sticks in my head was I got a call from a customer, and the customer said, "Hey, I got a problem with your simulator." I said, "Yes, what can I do to assist?" And this person says, "Well, my engineer, he put in some bad data, and simulator calculated and got bad results." And I figured, sounds like the simulator is doing the right job there. I mean, why aren't you putting good data in the first place? And a customer said, "Well, the simulator should know, hey, this is bad data," and then tell our customer, tell the user, "You can't use this data. It's bad." So yeah, I told him, like, yeah, well, if the computer could do that, then you don't really need to have like a process engineer running it, right? But when you use a simulator, it will tell you whether or not something is out of bounds, but it's not going to tell you that I can't flash my screen because you're above the critical point or something like that. It's at this point in time, it's still things aren't smart enough. So you put in garbage, you're going to get out garbage. It goes without that shouldn't be surprising. Yeah. Okay, so now let's go through some good habits, some things to do that we should think about before we start doing a process simulation. So incidentally, and I'm terrible at sales. That's why I've got salespeople helping me out. I've also what you're seeing over here is actually part of a book that I contributed for. It is called Process Simulation for Chemical Engineers. I think it's issued by Elsevier. There are two editions, edition 1, edition 2. For each one, I contribute maybe about like 4 chapters each. And one of the chapters starts off with this good habits of process simulation. There's another chapter which does thermal, which, it's great, I guess, if you can't go to sleep. I'm told that put a lot of people to sleep when they tried reading that. So let me start off 10 good habits of process simulation. Number 1. Good habit number 1. One of the most important things to do. Understand your objective. Now, you build a simulation model to meet an objective. No surprises there. So one thing that we do need to understand is your model is always going to be purpose-built. There's no one single mathematical model that's going to be able to represent all kinds of fluids and all kinds of processes. As a chemical engineer, you're going to, let's say if you're working upstream oil and gas production, you might need to work with like oils and gases. You might be sizing like compression trains. So you might be working with paraffins, methane, ethane, propane, etc. Non-polar components, which are primarily going to be in gas phase, which have like minimal liquid phase activity. So you might use something like HYSYS or Unisim. Use Penn-Robinson or SRK property packages for non-polar components. But let's say now you are concerned about the produced water and say, for example, MEG, monoethylene glycol that you might have been using for hydrate suppression. And you want to chuck that into a regenerator. You want to boil off this produced water and MEG. Of course, produced water is going to contain salts, electrolytes, and things like that. You can't use HYSYS out of the box. For that, you need to use something like Aspen Plus or OLI. So there's no one mathematical model that's going to be able to represent all fluids and all processes. Yeah. So the type of model and the level of rigor that you are going to implement, say, even if you're using HYSYS, You start off using HYSYS, and let's say you have a system, a PFD that you want to model, and there's some distillation columns. So you want to decide, hey, should I use like a shortcut distillation model, which is just using like a Fensky, simple Fensky relationship, or rigorous tray by tray, tray by tray flash calculation? Well, it really depends. So if you're just doing like a heat material balance, you might be able to use just a simple shortcut or Fensky model distillation column, or you might even use like a component splitter. But if you want to size the column and you want to take a look at flooding, then you need to have tray by tray because you need all the detail for each tray, how much vapor, how much liquid, vapor flows, liquid flows, and you need to be able to identify potential flooding or entrainment issues, flooding or weeping type issues. Number two, it's a good idea to make sure that you understand the system that you're working with, and that's to draw an envelope. So I know we've got some academics here, if not my good friend and partner, Professor Achao. I'm sure one of the classes that he teaches is going to be heat and material balance. And the first thing that you do when you're taught that class is to learn that, okay, this is my process. I'm going to draw an envelope around that, and I'm going to identify all the material streams coming in, all the material streams going out, energy streams going in, energy streams going out. Yeah. I always recommend for people like, for any of you that have done any kind of simulation work, you get a PFD or a PNID. And sometimes these can be very hard to follow. So what I always do, even myself, is I will go sketch it out by hand first. So I'll get a PFD, PNID, and I'll just turn that into like a block diagram or schematic, just so I know where things are going. And then I'll draw an envelope around the system to make sure that I'm capturing all the streams correctly. Yeah. So let me show an example of a case where we ran into a problem. Customer had a problem, and this could have been resolved very easily if they had sketched like an envelope around their system. So let's take a look at this. I've got a very simple system over here. And in this system, it's just like a water tank, a tank with some water in there coming in. Just look at this this setup over here. So I've got a system here where I've got maybe about a kilogram of air or gas or something, and 100 kilograms of water or liquid. And I find if I take a look at the, if I might have some flow meters, I might get about 100 kilograms of air coming out, but it looks like I got 120 kilograms of water. So what could be the problem over here? Well, this is actually what the issue was. And it was about drawing the envelope or bounding this. So in this more detailed sketch, we can see that this tank and this pump actually had a minimum flow recycle line. And the tapping point for the flow rate was at the discharge of the pump upstream of the valve, upstream of the level control valve. So you actually had like a minimum flow recycle coming in. So if you drew your envelope in the green envelope, you'd actually see that you'd get your material balance would comply with what you would expect. Yeah. So it is really, really important to know to be able to draw that envelope, particularly when you've got recycles in place. Okay, number 3. Now this is really important because a lot of times chemical engineering is the, I think, I would like to think it's the only discipline where we need to understand how things behave at a molecular or atomic level. That's our smallest building block, yeah? And then with that information, extrapolate up to figure out how this stuff is going to behave in bulk, yeah? So if you use a simulator, first thing you do is you choose what molecules you want, choose your property package, which gives you rules on how these molecules interact. And then you take it, you chuck it into a compressor, you chuck it into a pump, you chuck it in a distillation column, and then you see how it behaves. So we are going down from some very fundamental characterization of matter all the way up to very, very kind of bulk properties. So we need to be able to sometimes imagine how things are interacting because you must need to be able to describe the mechanisms behind the system or phenomena that you're studying. One things that I like to think about is, sometimes we look at dehydration. So how does dehydration work? When I say dehydration, I'm talking about gas dehydration upstream. So that's when you contact water, when you contact wet gas or water saturated gas with triethylene glycol. Yeah. So what actually happens there? Well, if you actually were to be able to look down at the molecular or atomic level, you would see that your hydrogen, your water molecule, which consists of 2 hydrogens and 1 oxygen, is polar. The oxygen part has like a negative, partial negative charge. The 2 hydrogen or the 2 protons at the end have a partial positive charge. Similarly, in your glycol, you've got an oxygen there with a partial positive charge, and you've got the rest of that, which is partial negative charge, and it's a large molecule. So you can imagine that to be like large, heavy magnets attracting your water molecule and keeping it in the liquid phase. So it makes, for me, it makes things easier to understand when I've got like some kind of a, like a cartoon image of that to kind of guide my decision making and to make allow me to understand things. So it's very good to understand. You might have to like imagine what mechanisms are taking place in order to really understand or get your hand around the phenomena or system that you're studying. Yeah. So here's an example like so let's say I have like a simulation model over here. So I've got like an inlet stream, I've got a valve or some piping or something like that. And then I run some fluid through, and I notice that I've got a pressure drop, and accompanying pressure drop, I see a temperature drop as well. So initially, if I'm doing heat material balance, I might be wondering, why is there a temperature drop over there? I don't have a heater or cooler. Then I remember that, okay, in this case, what's happening through the valve? I'm getting some kind of an expansion. As I get some kind of expansion, even though this is adiabatic, I have some cooling effect. Why do I have some cooling effect? Well, as we know that there's some attractive force taking place in between molecules. So when you're expanding the gas, the effect of the attractive force trying to fight against the expansion of the gas actually may result in small areas where the energy of your fluid might fluctuate. You might not get like an overall bulk effect, but you might get like small areas where you do have energy changes, which are not captured by your standard equilibrium model, and that can manifest itself in terms of a temperature drop. Yeah. So this is the Joule-Thomson effect. What I've described is just the Joule-Thomson effect. So we learned in thermal that, when you put something across a valve and you have an expansion, you get a temperature drop. So it's a good idea to understand why would there be a temperature drop and relate that with the intermolecular forces, your attractive forces. Yeah. So that helps me understand and appreciate things more. And I would assume for most other engineers, that would be the case. Number 4. So this is the part, this is why we spend 4 years of engineering school. This is why we, for those 4 years, we've slogged through all of these courses and exams and gone through thermodynamics, transport phenomena, which is momentum, heat, and mass transfer, reaction engineering, and we've done our unit operations, heat exchanger design, our capstone project, where we've probably designed a facility. We need to understand what sort of mathematical framework we need in order to represent that physics-based model. Yeah. So this is important because ultimately, when you use a simulator, it's all mathematical models. So you need to know what is being utilized in your simulator to make sure that you understand that that simulator will be able to execute whatever kind of computation you need. So here's a simple example. If you want to take a look at the phenomena of water hammering, and This is one, if you're, let's say, like an upstream facility, you've got like a water injection system, you're transporting water from your deaerator to your pumps. If you suddenly close a valve, the water which is flowing suddenly stops flowing, and then you suddenly get a change, a sudden deceleration, and that manifests as a change in momentum, and that then manifests in terms of a pressure wave, which kind of goes back and forth. Yeah. So that kind of phenomena is fluid mechanics, momentum transfer, the change of kinetic energy into pressure. And that's not represented in thermodynamic steady state or even thermodynamic-based dynamic tools like HYSYS. You can't use HYSYS for that. Can't use UNISYP for that kind of phenomena. You'll have a product like a PipeNet, which will allow you to take a look at phenomena like liquid surge or water hammer or rapid momentum transfer. Yeah. Okay. So you need to use some other tool. Now, I found out the hard way when I was younger. I think one of my sales guys told the customer that, yeah, we could use HYSYS for water hammer and liquid surge, and obviously we couldn't, and ended up having a very angry customer. Yeah, so you're going to find one thing, like you have a lot of different kinds of engineering activities, and you're going to find that you have a lot of different tools. So for heat and material balance, you've got all your standard flow sheeting tools like HYSYS, Probe 2. For piping, you might have like a Flowmaster SPS, PipeNet, multi-phase, dynamics. If it's high multi-phase transit, you might have something like Olga. Heat exchanger design, you might have EDR or HTRI, tools like that. So you got all these kinds of different tools, all these different kinds of options. And you're always going to be wondering, what software am I going to use? And people used to call me all the time and say, hey, you used to work for SimSci, used to work for Hypertech, used to work for AspenTech. What's better? Is HYSYS better than Pro 2? And the answer is, really, it depends, and depends on what you want. So one thing that you need to be careful of, though, is software salespeople. Anyone that's trying to sell you stuff, generally the main objective is to make as much commission as they can. So they're going to tell you, yeah, my software can do water hammer, and at the same time, you'll probably make toast. So you need to be a bit careful. Scrutinize a software application to make sure that it can do what you want it to do. If you can get the operating manual and run through and see what kind of equations they're using, what kind of physics models they have. That's generally what I use. In my case, it's kind of specific because it's East 101 is my own company, and I'm in charge of the budget. So I'm not going to buy a piece of software until I'm sure that it absolutely can do what I need it to do. Okay. Good habit number 5. It's really important to identify the components that are going to be involved and what kind of interactions they're going to participate in. So you need to understand how they're going to be interacting with each other. And based on that, you'll be able to figure out what kind of property package you need to use. It's very interesting. It's very important. Let's say I wanted to model a methanol plant. So let's say I was doing some work for, say, Methanol Labuan, Petronas methanol plant in Labuan, where they are synthesizing methanol, where they're making methanol. So they've got the reactor, you're making methanol, then you have to separate the methanol in the water in the column. So in a case like that, I'd be interested in the liquid activity type model, because there's going to be a lot of liquid activity in this case with methanol and water. When I separate them, I've got all these hydrogen bonds. But if I'm using methanol for hydrate suppression, where I've got methanol and I have like a hydrocarbon stream more than gas stream, and I'm chucking in methanol when I start up a well to avoid, when the temperature comes down, I get this chilly choke effect, which can result in hydrate formation or solid formation. I chuck in methanol there to prevent hydrates from forming. I can't use these liquid activity coefficient models. Instead, if I'm using HYSYS or UNISYM, I think nowadays they use CPA, cubic plus association models, to address this. In the old days, one would use HYSYS Peng Robinson, because back in the old days, Penn Robinson had all of these structure built in to represent hydrate suppression in the presence of methanol and glycols. Yeah. So you need to understand what kind of phenomena is going on. Because even in this example, I've got methanol and I've got water, but I have to use two different kinds of fluid packages because the behavior that I'm looking at are two different types of behaviors. If you're working with salts or ionic systems, then you might need to use something like Aspen Plus. So your, I think it's called electrolyte NRTL, ENRTL in Aspen Plus, or to like a OLI for electrolytes. Okay, good habit number 6. Now this is really important, I think, for all areas. So I noticed that there's some people from from some refineries over here, and the characterization of your refinery feedstock is non-trivial. Your crude oil contains about 30,000 different components, and you need to make sure that they're characterized accordingly, because you're not going to punch in 30,000 different molecules in there. They're going to use like a TBP curve, true boiling point curve, or ASTM curve, and you're going to have to utilize that to create pseudo components or hypo components. Well, sometimes your curves might not be complete. You might only have a curve up to about 70% or 80%, and you have to do some extrapolation. So you need to understand maybe what kind of crude this is, and maybe get some past examples to see what you can do to help extrapolate to the endpoints. If you are working upstream and you're looking at crude oil production, sometimes when you take a look at the gas analysis, when you've got your initial separator, you've got crude oil, you've got water, you've got gas. If you've got your gas stream coming out, you look at the analysis, and it's from a GC analysis, gas chromatography system. So your gas chromatography GC analysis will not contain any water, because you need to knock all the water out before you put it into your GC apparatus. Hence, the analysis that you get is going to be dry. It's going to be bone dry. You won't have any water inside it. But, in reality, if this is coming from upstream, that you do have some water in your system, hence this gas would be saturated. So if you wanted to perform a simulation for this system, even though you have this upstream separator, even if your gas composition is bone dry, it's 100% dry, you need to look at the temperature and pressure of the system and determine how much water this would actually contain. Yeah, so you'll very seldom are you going to have a gas composition with like no water inside. So the numbers that you get sometimes in the reports are kind of artificially dry because of the analysis requirement. Okay. Good habit number 7. This is just something that I typically would do. And at the end of the day, if you're a chemical engineer, you're generally going to be, one of the things that you're going to be doing a lot of is vaporizing and condensing things. Yeah, you do that in distillation all the time. That happens like when you're in a flash drum or anything like that. So for me, if I want to do a quick and dirty heat material balance, what I typically do is just arrange everything in terms of the boiling points. Then I can draw a line. Yeah. So I think for most of us, if you've done distillation class in the chemical engineering school, you might do like a simple calculation, like a Fensky-Underwood calculation, where you have to identify like a light key and a heavy key. So it helps if everything is like arranged in the order of the boiling point of increasing boiling point. So you can do that. You just draw. Let's see, if I had like the propanizer, I can just draw a line over here and say, okay, all the propane and lighters go on the top, maybe a bit coming the bottom, and most of the butane is coming down the bottom. Yeah, so it's important to know the components, boiling points of the system that you're working with. Number 8, This is very, very important. And I think all the academics over here will be stressing on this with their students. You need to make sure that you keep track of your units of measure. Yeah, even my engineers, when I'm talking to them, if we're having lunch or something, there's a calculation they're doing on a dirty napkin, they still have to put the units of measure. Because in oil and gas, unfortunately, we work with a huge range of units depending on what countries you're going to be working for. Yeah, if you're working for an American company, if you're consulting for an American company, they're going to be working in imperial units. If you work for like an Asian company, a Japanese or Korean company, everything will be like in SI. So you need to be able to switch back and forth. Okay. Good habit number 9. This is something that I'm always telling people. You need to be able to perform a simple heat and material balance first before you even fire up the simulator. So I do some advisory for some of the universities on some of the advisory panels, and I help teach some of the run some workshops for students when they're doing their capstone project. And one of the things that I tell the students, before you run a simulator, make sure before you actually punch things into the simulator, do a hand calculate material balance first, so you get a feel for the magnitude, order of magnitude of some of the numbers you're going to be working with. So here's like a simple example. I've got a depropanizer column. Yeah, so you might be modeling this on HYSYS or Unisim or any other tool. And I'd say about 99% of the complaints that I will get from my clients or my students is, hey, I can't get this thing to converge. So in this case, I've got like a column with a condenser and a reboiler. So I've got 2 degrees of freedom over here. And the 2 degrees of freedom have been consumed by the reflux ratio and an overhead propane mole frac. So according to this, the user wants the propane mole frac to be 95% or 0.95. And they're running it, and it just won't converge. So what happens, sometimes I'll sit down there and I'll watch my students do something, it won't converge, they'll hit reset, run again, reset, run, in hopes that it will converge, but it never does. Then they might change specs arbitrarily. So we want to stop that kind of random troubleshooting. Yeah. So let's take a look at the system over here. Why can't I get this converged? Got that red sign that's not happy. Yeah, my equilibrium, my heat and spec error, I'm not converging. It says, well, equilibrium seems to be doing okay, but I've got my heat and spec error aren't converging. Hence, my spec, my desired specification of 95%, I can't meet that here. So what I'm going to do is I'm going to do like a simple material balance first. And let's take a look at what I have here. So I've got my feed, and this is what I have in my feed. So I've got some methane all the way up to normal butane. So what I'm going to do over here is what I do in school. I'm going to figure out what's my light key and what's my heavy key. So I'm going to say propane and heavier going up, propane lighter going up, and the heavier molecules going down. Yeah, I'm just going to draw a line, just like a simple ideal thing. Propane lighter goes up. And I know this, if I send all my propane at the top over here, there's no way I'm going to get 95% propane. Why? Because I've got methane and ethane as well. So I can only get about 35% propane at the top at the most. Yeah. So that's not going to happen. So the issue over here, yeah, I'm not going to be able to meet this because I can't meet the material balance as it is. So it's really important to do like a quick hand calc first. Okay, we'll go to the last one. This is important as well, is to make sure we plot the phase envelope for important streams. So this should be a reflex for all engineers. It's really important because you need to keep track of where your dew points are. If you've got feed going into a compressor, you want to make sure that you don't have any liquids coming out. If you got feed into a pump, you want to make sure that your liquid is subcooled so you don't get any potential cavitation. So it's good to be able to plot your phase envelope. And what I would typically do is I would just plot it and stick it up at my desk to make sure that when I'm doing the simulation, I check the pressure and temperature and I see where I am on the phase envelope. So let's take a look at this one example, over here. So this is a simple case. I think if you've taken my class before or any other class on HYSYS or Pro2, this is the classic dew point control unit where I have a rich gas coming in and I'm chilling it to check out to remove the heavy ends so I can have a leaner gas and control its dew point. So in this case, I want to know what is the dew point pressure of this stream, which is at 20 degrees Celsius. So I have a stream at 20 degrees Celsius. I want to find out what the dew point pressure is. So if you're like a HYSYS or Unisim user, this would be quite straightforward. You punch in the temperature and you punch in vapor fraction equals to 1. And you will get your dew point. So according to this, it's about 29 bar. Yeah, 2,962 kilopascals. So it gives you a number. And what I'm going to do now is, okay, that's interesting, but let me plot the phase envelope and see what this looks like. So I go to the phase envelope attachment thing and I generate the phase envelope and I get this. And I get this number, which is about 29 bar, which makes sense. Yeah, at minus 20 degrees Celsius. But I realize when I look at this diagram that I actually have two solutions. So in this case, I've got like this fat or bulging region, and that's a retrograde region. Yeah. So if you remember from the thermo class, if you've got components whose boiling points range from really, really light, like methane, about minus 162 degrees Celsius, all the way up to like really heavy components with boiling points of like over 200, 300 Celsius, you can get phase behavior that looks like this. Yeah, this retrograde region. Yeah, what it means is some components are some of the molecules are at their critical states where some other molecules aren't. That's why you have a bulge. Normally, you would expect to see like if you have like a leaner compositions, like a thinner, a thinner phase envelope. So you would only, if you use HYSYS, if you use this and you punch in 1, you'll only get 1. Sorry, if you use punch in minus 20, you'll only get 1 point, but you'll only see this retrograde dew point if you plot your phase envelope. There's actually a numerical trick in HYSYS. If you put -1 instead of 1, you will get the retrograde dew point of about 80 bar. So that's like a little trick. But I don't think it's documented anywhere. Okay, so that concludes the presentation. And just to summarize things with these 10 things to do before I stop to take some questions. First thing we need to do is make sure you understand your objective, and that will allow you to decide what kind of tool or mathematical framework you're going to use to solve it. You need to obviously identify your system, draw an envelope, know what's coming in, what's going out, material as well as energy. Helps to imagine what mechanism is taking place. Yeah, interactions, like, for example, hydrogen bond interactions, dissociation, just have an idea of what's going on. It's also important to be able to at least remember some stuff from university to allow us to understand what kind of mathematical models are coming into play when we're looking at different types of physical phenomena. Yeah. The fifth is to identify the components that are involved and what sort of interactions are taking place so that we can choose a property package. Yeah? 6 is to understand the context of the feed streams, characterize them correctly or adjust them correctly, add some water, or extrapolate the endpoint boiling points. Understand what our components' boiling points are so you can arrange them in nice order. Number 8, keep track of your units of measure. I remember when I was in engineering school, if I didn't properly do the unit equation, if I didn't cancel things out, I would get my points docked from that solution. Make sure we always perform a heat material balance first, and always make sure that we plot the phase envelope for important streams. So that's all that I have to say. I'd like to thank you all very much for your participation. Yeah, I'd like to take any questions you might have. Yeah, I'll open the floor for questions.
Okay. So, engineer,
Yes, sir.
thank you very much for such an information section. And then, as you said, we've opened the floor for question. Whilst we are waiting for the question, someone would wonder, where is this one coming from? So this webinar series, it's not just one out of the blue or once in a blue moon webinar. It's something that we will be doing it once in a month. So if you happen to get in touch with our LinkedIn page, EBL Engineering and East 101, you look out for such events, and then you check your email for subsequent invitation to similar webinars. And once again, someone would ask, what is EBL Engineering and then East 101? So EBL is simply a specialized engineering limited or a limited liability company in Ghana, which specialize in providing operation strategies and performance management. Anything that has to do with process design, plant design, equipment design, applied chemical engineering, process safety services. And we do this with our partner, East 101. That is the team with us today to do this webinar. So aside this webinar, we are open to help you solve all your process engineering challenges, performance improvement, and anything that has to do with improvements, startup design, anything troubleshooting, we are there to assist you. So I'll drop my email in the chat, and then you look out for our pages on LinkedIn, East 101 EBL Engineering Limited, for more information. So I'll be waiting for your question in the chat in the next 2-3 minutes. If not,
I think there's a question from Ng Sheng Tat.
Yeah. Please, I want to know whether this applies to all process engineering design and operations.
Yeah. We have a
From
question
Robert.
before that, Ebenezer, from Ng Sheng Tat.
Okay. Good evening, sir. Thank you so much for sharing. May I ask if I am interested to build competency in process simulation? Apart from book written by you, is there any recommended books? I am more interested in the areas such as thermodynamics, fluid dynamics, transport phenomenon, equipment sizing and design, reaction, and then reaction engineering.
Okay, thank you very much, Ebenezer. Thank you very much for your question, Mr. Ng. Now, there are tons of good books out there, but I can only tell you what I use myself as my reference, my go-tos for that, and my go-tos might be really, really old for thermodynamics. I still every now and then refer back to my college textbook, which is Smith and Van Ness. But I find for day-to-day work, one of the best books I have is, unfortunately, it's out of print. It's called Wallace, W-A-L-A-S, by Stanley Wallace, and that's Applied Thermodynamics. I don't know if you can still find it. I've also got Proutznitz, Poling, and Reed, and that's a bit more theoretical, a bit more physics-based. So these are my three go-to books: Smith and Van Ness, Proutznitz, and Wallace. That's for thermal. For fluid mechanics and transport phenomena, again, I go back to my old uni book, which is Welty, Wicks, and Wilson. And if I want a bit more physics representation, I would use Bert Stewart and Lightfoot. Again, these are all old, I guess, go-tos. These are books that have been around for like decades. Equipment sizing and design. I think I'm using McCabe and Harriet or something. Again, that's what I use in college. But I think there's a lot of different kinds of books you can utilize these days. But I find that those give me the best representation. And maybe it's just because I'm used to them and I know where to find things. Reaction engineering, I typically use, again, from uni, Levenspiel. Yeah. So I think one can find a lot of different books these days. And I think now it's also a bit of a mixed media learning, because in addition to books, sometimes I go up to YouTube and I listen to people talking about things. So I think everyone's quite lucky these days with the technology. There's a lot of places we can learn about things. Yeah. So I hope I answered that question.
Yes. The next one.
Shall we go to the next one?
Please, I want to know whether this applies to all process engineering designs and operations.
Okay. This is from Mr. Robert Nyamike. Am I pronouncing it right, Ebenezer?
Yes, Mr. Robert
Okay.
Nyamiche.
Okay, Mr. Nyamike. So, well, I put this specifically for the example specifically for process engineering. Yeah, as simulation in particular, and I'm sure it's going to be applicable for most types of process engineering type activities. But as you notice, like some of the things here are very specific for process simulation, like the thermodynamic models, etc. But I think these are just 10 things that I would do before I embark in any kind of a design. Actually, these are 10 things that I would do before I even decide what kind of simulator tool that I want to use. Yeah. So I would say that this would apply to probably most of your process engineering design activities. Yeah. I actually put together like a version 10 things to do before any kind of scientific activity. And I gave that to my daughter before she went to university. She studied biomedicine. So I converted all of these things into like some kind of a generic 10 good things to do before you're solving some kind of a scientific or engineering problem, which is a very, very generic version of this. Okay, so I hope I answered your...
Yeah. The next question is, thank you very much for such an informative webinar. I have missed the trick point to find out dew point by using one instead of one. I would appreciate if you can repeat.
Okay, so yeah, it's
minus one instead of one.
Yeah. So if you have a fluid which exhibits retrograde behavior, there will be two dew points. Yeah. Maybe I can just share. Let me share back my screen if I can get that slide.
I don't know. Before we go to that screen, I think there is a follow-up question from Yamiche. I am asking this question because I want to apply them in simulation of process in wastewater treatment plant.
Okay. Yeah. You can. I mean, what I was describing here, these 10 things to do would probably be applicable to that activity as well. Doing a material balance, drawing an envelope. These would be applicable as well. Yep.
Okay.
So shall I share my screen?
No, you can share your screen.
Yeah, okay. Okay. It's my phase envelope. Okay. So let me go back to the phase envelope over here. Can everyone see the screen okay?
Yes, I can see.
Okay. Oops. Yikes. Go back. Sorry, yeah. Okay. So if you take a look at this case over here, I actually have two dew points. One over here, this is called my dew point. This one, I'll use the term dew point to describe this. And this dew point here occurs because of the retrograde region, because you have this bulge. Yeah. So if you take a look at the system over here, normally if I look at if you draw your phasor envelope, you might expect kind of drawing this with a mouse, so it's not really that specific, but you'd have something maybe which kind of looks that's not very good. Let's see, erase all this. Yeah, maybe something which looks a bit more like that. So you don't really have a bulging area. You've essentially got like a critical point, which is the maxima. But now you can see a critical point is over here. Yeah. And you have like a pressure maxima here and the temperature maxima here. So because of that, you've got this bulging. So this point no longer denotes the maximum temperature and pressure of your system. But instead, your critical point has split into like a maximum pressure point or Crichton bar and a maximum temperature point or Crichton therm. So that causes this bulging behavior here. So normally you would just have, normally it might just look like something like this. And you might just have like a single dew point. But because of this bulge, you have a dew point here and a dew point here. So this is generally called the dew point. And this second dew point, which arises because of the bulge, because of the decoupling of the maxima into a pressure and temperature maxima, this is referred to as the retrograde dew point. So you have two dew points. So if your system exhibits this retrograde behavior in HYSYS or Unisim, if you punch in 1, you see this, a blue 1 and a blue -20, it will calculate the dew point pressure for you. If you punched in -1 into this case, you would get 8,000. Yeah, so that's just as strict. So if your system, if you know that your fluid exhibits a retrograde dew point, you can punch in -1 for HYSYS to exhibit that. Yeah, so that's all this little trick was. I think I put that in my LinkedIn, if I'm not mistaken.
Okay. So, engineer, thank you once again for this insightful webinar and then discussion. And I think I'm about to close and then there is more question.
Is there anything else?
Okay, he was thanking you for the explanation.
Oh, okay. Thank you. Thank you so much, everyone.
Okay.
And thank you so much for organizing this, Ebenezer and Prof.
So thank you all for joining today's webinar, and we hope you found it valuable. And if you have any further question, kindly feel free to reach out to me. I've dropped my email in the chat box. So thank you, and then look out for more webinar series. And if you need any process simulation assistant, anything that has to do with applied chemical engineering performance improvement, kindly feel free to connect with us. We will be more than glad to assist you. Thank you all.
Thank you all. Everyone have a great weekend.
Okay.
Yes,
Thank you,
so bye-bye. Engineer Raphael, has been a wonderful presentation. Thank you very much.